Valence bond theory is widely accepted to understand the bonding in molecules. The theory says a covalent bond is formed between two atoms by the overlap of atomic orbitals of each atom containing one unpaired electron, the valence electron. The inner shell orbitals and the electrons remain unchanged. There are two types of orbital overlaps, sigma bond and pi bond. Sigma bond is a single bond formed by head-to-head overlap of orbitals. For example, SS overlap, SP overlap, PP overlap. Pi bond exists in a double bond or triple bond. Pi bond comes from the side-by-side overlap of orbitals. See the graph at the bottom on the slide. There are one sigma bond and one pi bond in a double bond. Analogously, there are also one sigma bond, but two pi bonds from side-by-side overlap of orbitals. The experiments confirmed that a molecule methane has a tetrahedron structure. 4 CH bonds are the same in length. As shown at the bottom of the slide, there are only 2 unpaired electrons available in carbon atom, which means only 2 covalently bonding is possible. But in fact, there are 4 bonds in methane. How can we understand the bonding in methane? The valence bond theory presents a new solution to this problem. It's a hybridization of the orbitals. The valence bond theory suggests that the orbits in carbon gets hybridized. One 2s orbital mixed with 3 p orbitals produce 4 hybridized orbitals called sp3 orbitals, which has a shape of a tetrahedron. Each of the 4 sp3 orbitals points to the corner of the tetrahedron. The 4 sp3 orbitals are degenerated, or say equal energetically, covalently bonded with 4 hydrogen respectively. You see, the concept of hybridization of orbits explains the tetrahedron structure of methane perfectly. Other types of hybridization are also suggested and employed to explain the chemical structures of molecules, as shown here. sp hybridization, it supports a linear structure, sp2 triangle structure, sp3, as you see in methane, tetrahedron structure, and etc. We should be clear that the hybrid orbitals have lower energy or energy levels compared to the pristine orbitals. As shown here, in sp hybridization, one s orbital hybridized with one p orbital forms 2 sp hybrid orbitals. sp orbitals, the energy level of sp orbitals is lower than that of non-hybrid p orbitals. Analogously, in sp2 hybridization, the energy of sp2 orbitals is lower than non-hybrid one. Briefly, in the same way shown here, we can understand all the hybridization. Let's use the concept of hybrid orbitals to explain the structure of ethylene. As you see on the left, a molecule structure has 2 triangles with carbon at the centers. sp2 hybridization corresponds to triangle structure. When the hybrid orbitals of carbons begin to overlap, one of the sp2 orbital from one carbon overlaps with sp2 orbital from another carbon in head-to-head way, forms a sigma bond. the non-hybrid pz orbital from the two carbons overlap in side-by-side way forms a pi bond. The four sp2 orbitals form sigma bonds with four hydrogen atoms. Again, valence bond theory shows its power to decode the chemical structure.